So, hi everyone. My name is Dr. Shabarinath, working as an assistant professor in the EC department from VNR VIGNAN JYOTHI. So, today I am going to present about computer arithmetic. In this, as a part of this lecture, I am going to present about fixed point computation of addition and subtraction when the data is represented in fixed point. So, before starting this, let us continue. Let us start with this. Now, okay. First of all, the solution to any problem that is stated by the finite number of well-defined steps, that is called an algorithm. Okay. So basically, this any algorithm consists of number of procedural steps. Okay. So which are dependent on the results of the previous steps. So the convenient method for this representing this algorithm is a flow chart. Okay. Now, so in this flowchart, basically what we do is we represent computation using this rectangular box. All the computational steps we represent using rectangular box, as well as the decision making steps we represent using the diamond shaped box, where we have two or more we can take the decisions alternatively. Now, in order to explain this flow chart, we are going to explain with the help of in order to explain this algorithm, we are going to explain with the help of this flow chart. Okay, so let us start with this first algorithm, that is addition and subtraction. Okay, so addition and subtraction algorithm, in this case, first the data, whatever the data is represented in the fixed point format. Okay, so fixed point format, as you know that fixed point can be data can be represented in three ways. Okay, one is sign magnitude form, one's complement form, and two's complement form. So in this algorithm, we are representing the data using the sign magnitude form. So in this sign magnitude form, as you know that we represent sign and we use one bit for representing the sign, and the remaining bits we are so this bit is used for representing the sign, and the remaining bits are used to represent the magnitude. Okay, so before proceeding with this algorithm, so let us start understanding this first of all. So for example, let us take 4-bit numbers. Okay, let us take 4-bit numbers. So suppose if the range is 4-bit, so this unsigned numbers can be represented from 0 to 15, as you know that. Okay, so before proceeding with the algorithm, I'm trying to explain some basics here. So the first thing is, let us take any two unsigned 4-bit numbers, and let us try to perform the unsigned subtraction. Okay, so unsigned subtraction, for example, let us take these two numbers. Okay, 9 minus 4. Let us 9 minus 4, as we know that the result is 5, right? So how to represent 9? You know that 9 is represented as 1 4 0 1. 4 is represented as 0 4 0 0. Now, so the same unsigned subtraction I am performing using the 2's complement method. So in 2's complement method, what we do, this negative number is represented in the 2's complement form. So as you know, what is this 2's complement form? If we follow this procedure to find the 2's complement of 0 1 0 0, so we use this shortcut method, like so whatever the zeros we write, so whenever the first non-zero digit we'll write as it is, from next onwards we complement. So this is the complement of 0 is 1. So this is the 2's complement of 0 1 0 0. Now what we can do is unsigned subtraction. So instead of performing subtraction, we can perform the addition. The 9 is 1 0 0 1. So the minus 4 is 1 1 0 0. Okay, let us perform the addition for these two numbers. So 1 0 1 0 1. So you can observe here we got a carry. So here we got a carry. Okay, so generally we ignore the carry to interpret the result. So here the result is nothing but plus 5. Okay, you know that, right? 0 1 0 1 is nothing but plus 5. But here I want to convey this point. So if we get a end carry, the interpretation here is that 9 is greater than 4. Okay, so this is the interpretation here. So if we perform the unsigned subtraction using the 2's complement addition, so using this method for the unsigned numbers, what we interpret is if we get a end carry, we can tell that the first number is greater than the second number. So this is one of the result. Okay, so let us do the next thing. So let us try to do this next thing, like for example, if we want to do 4 minus 9. Okay, now you know that the result is minus 5. So we apply the same method here. So for example, 4 is represented like, okay, a 4 this one. So similarly minus 9 is represented, first represent the plus 9. Okay, so then you take the, since it is a minus 9, take the 2's complement of this. So 2's complement, first you write you proceed this way, right? First write the non-zero till the non-zero digit. So whenever you the remaining digits you complement, so 1 1 0. So this is the 2's complement of this. Now you try to perform the addition. So 0 1 0 0, so 0 1 1 1. Okay, if you perform the addition, so 0 plus 1 1 0, carry is 1 1, so final carry is 0. So here, okay, first of all let us see the thing, like here we got this. So the interpretation is that it's a negative number. To want to get the magnitude, take the 2's complement of it. So 1 0 1 0. So this is nothing but minus 5. So but here I am interested in not in the result. So I am interested in this result, like if I get a carry as 0, then what is the meaning is, like the first number here, the 4 is less than 9. Okay, so let me so based on these two results, what I can say that if I, for example, if I generalize this, if I perform the unsigned subtraction using the x plus like 2's complement of 5. Okay, if we do this method, so if I get a end carry, I can tell that x is greater than or equal to y, right? Or if carry equal to 0, I can tell that x is less than y. Now this is the one of the result, very important result, which we are going to use in this algorithm. So why this is important means, so in the design of the computer hardware, here you, instead of using the comparator, by using this 2's complement addition method, we can compare the two numbers, and based on the end carry we can tell that whether the first number is greater than the second number. So here instead of this the comparator operation can be replaced like this. The comparator work can be done like this. So this concept we are going to use in this algorithm. Now let us start with this first algorithm. This is the algorithm, right? So in this algorithm, what we are trying to do, we are trying to add two numbers. We are trying to develop an algorithm for performing addition and subtraction of two numbers, right? So the two numbers are represented in the sign magnitude form. As you know that as you know in the pen paper method, what we do, like we get a total 8 different combinations. Like for addition, what we know, so for addition, if we want to do addition, we may get a first number as positive, second number as positive, first number as positive, second number as negative, first number as negative, second number as positive, and first number of negative and second number as negative. So these are the 4 combinations for addition, right? Similarly for subtraction, we are going to get the 4 combinations. Now you can see here, in case of addition, if the signs are different, sorry, in case of additions, if the signs are same, okay, if the signs are same, okay, positive positive, negative negative. Similarly in case of subtraction, if the signs are different, in case of subtraction the signs are different, okay, we can perform addition, we can perform the addition, right? So here we can perform the addition. right? So this is the first observation. So what we are trying to do is, I am trying to develop an algorithm for performing the addition and subtraction of the sign magnitude numbers. So we need to define a unique algorithm such that we can able to perform both addition and subtraction as well. For that, what we did, we have written the 8 possible combinations for this. So in these combinations, we understood that if the signs are same for subtraction, for addition, in case of addition, if the signs are same, similarly for subtraction, if the signs are different, what we are trying to do, we are trying to add these numbers, right? And we are keeping the same, let us take the reference as a. If we take the reference as a, what we are trying to do here, the sign of the result is nothing but the sign of the a. You can observe here, the sign of is nothing but sign of the a in this case, also, in this case also. Okay, so this is the first interpretation of the of this. Okay, so if the in case of addition, if the signs are same, in case of subtraction, if the signs are different, we are trying to add these two numbers and we need to keep the sign as sign of a. Okay, similarly, let us proceed with this. Now you go for the like in case of addition, if the signs are different, in case of subtraction, if the signs are same, what we need to do, we need to perform the subtraction. So what kind of subtraction we need to do again? See here. So again in this case, what we are trying to do, for example, take this. If the signs are, in this case, sign of A and sign of B are different. So what we need to do? We need to do subtraction. So again here we get a 3 cases. What are the 3 cases? So we may have A is greater than B, or A is less than B, or A equal to B. Suppose A is greater than B. What I need to do? I need to perform A minus B and I need to keep the sign as A, right? Similarly, if B, A is less than B, what I need to do? I need to put B minus A, then I need to keep the complement of sign of A, right? Similarly, if A equal to B, I need to make A minus B and make the sign as positive. Listen here, what I am trying to tell is, so here we are if the signs of the two numbers are different, in case of addition, what we need to do? We need to first compare the two numbers, right? So what comparison we need to do? We need to identify whether the first number is greater than the second number, or first number is less than the second number, or first number is equal to the second number. So after identifying this, what we need to do? We need to subtract the larger number, right? And from the so we need to subtract smaller number from the larger number. So in this case, the smaller number is B, so we perform A minus B. Similarly, in this case, the smaller number is A, we perform B minus A. So similarly here also. But what about the sign? The sign is nothing but, okay, whatever the larger number is there, that sign I can take, or I can define like this. For example, if you subtract, if A is greater than B, the sign of the result is nothing but same as the sign of A. Okay, or if A is less than B, the sign of the result is nothing but complement of sign of A, right? Complement of sign of A. Okay, now let us define the algorithm, right? Now see here, if the numbers are equal, what is the sign we are taking? So if the number are equal, we need to ensure that we get the positive 0, right? So for that, we need to take care about that, right? We need to take care that we don't get a negative 0, right? Now let us define this algorithm. So what is algorithm? So the algorithm is that, okay, so for the algorithm is that, so when the signs of A and B are identical, okay, are different, so identical in case of addition or different in case of subtraction, what we need to do? We need to add the two magnitudes, right? We need to add the two magnitudes, and sign of the result is nothing but sign of A, right? This is the thing, right? And the if the two magnitudes are equal, what we need to do? We just subtract and keep the sign as positive, right? So similarly, if the signs of A and B are different in case of addition, and signs of A and B are identical in case of subtraction, what we need to do? We need to subtract the larger number from the smaller number from the larger number, and if A is greater than B, the result of the sign is same as A. If the A is less than B, the result of the number, the result of the sign of the result is nothing but the complement of sign of A, right? So this is what, okay, so this is what the algorithm we have defined, right? So based on this algorithm, if we proceed like this, what happens? What is the estimated hardware we get? So if you observe carefully, the estimated hardware is that we require an, if we want to perform, right? So the subtraction I can do, okay, the subtraction, okay, I need to perform addition and subtraction. So for performing addition I require an adder, right? Similarly for performing the, okay, for doing this comparison I require a, whether a less than b, okay, let me, so for doing this comparison, a greater than b, a less than b, a, so for doing this comparison I require an, I require a comparator. So this is one thing, I require a comparator. Now again for performing addition, okay, to do this micro operation I require an adder, okay. Similarly here I need to do a minus b as well as b minus a, right? So for doing a minus b I require one subtractor, okay. Similarly for doing b minus a I require one subtractor, okay. Also what I require to decide the sign, right? To decide the sign I require an XOR gate. You know that we can use XOR gate for defining, for deriving the sign, right? For identifying the sign of the result. So what we require one adder, two subtractors, one comparator, one XOR gate, right? So if we proceed, if we think like this, we require this much. So is it a optimized way? So this is not an optimized way, right? Okay, to ensure the less amount of hardware, what we do, we optimize, we think in a different way. So what we do is, so instead of this, we know that this subtraction and addition both can be done with the help of a 2's complement method, okay. So instead of one adder and two subtractors, we can use only one adder and one complementer, alright. So another thing is, instead of this comparator, what we can do, we can use the same 2's complement subtraction, and we can able to decide the whether a is less than b or a is greater than or equal to b based on the end carry. So we can avoid the, so using this 2's complement addition method, right, 2's complement subtraction using addition method, what we can do, we can avoid the use of comparator. Also instead of one adder and two subtractors, we can use only one adder and one complementer. Also we can use one XOR gate, okay. So based on this technique I explained here, based on this technique I can explain here where I can use this 2's complement method as a comparator. So using this method I can avoid the hardware, I can able to minimize the hardware, right? So finally so this is this is what I told. So if we use the without optimization, like we require all this hardware, right? So but instead of this, what we can do is, so we can perform this subtraction, right, comparison using this 2's complement method, right? So this requires less amount of hardware. So let us see this, what is the hardware, right? So see here, so this is the hardware for our implementing our performing our the sign magnitude addition and subtraction, right? So one of the input is there in the A register, you know that, right? In sign magnitude form we store the sign separately and we store the data separately, the magnitude separately. The magnitude of the one number is stored in the A and the sign is stored in the AS. This is the sign, okay, this is the sign bit. Similarly we have another input stored in the B register, right, and the sign of this is stored in the BS, right? Now you see here, the next thing is the complementer. You know the functioning of the complementer, that how this complementer works. If m is equal to 0, okay, the output of the complementer is nothing but B, right? Just transfer this B, right? You know that complementer is implemented with XOR gate. This I have already explained in the first unit, right? How we implement this complementer, right? So if m is equal to 0, just B is transferred, right? But if m equal to 1, what happens, right? So okay, if m equal to 1, what happens? So this complementer will output B 1's complement, B complement, right? Now what is this thing, what we need to do? So actually our intention is that also this complementer output is connected to the parallel adder. You know this, see here, this parallel adder is able to add the one of the input to this parallel adder is the content of the A register, another input to this parallel adder is the output of the complementer, and the result of this parallel adder is stored in the S, okay. Similarly the result the sum result is stored in the A register. Similarly the carry is stored in the E. Now see here, what is how this hardware works, you need to understand this way, okay. So what you need to understand, first of all, if m equal to 0, what happens, the complementer output will be B, right? So this A, so what your parallel adder will do, so parallel adder will be able to perform A plus B and the result is stored in the A. So this is a micro operation performed, right? Similarly, if m equal to 1, what I told, this will be the B complement. Similarly, m equal to 1, right? So since the external carry, this m is also given as a external input carry to this parallel adder. So what happens? So it will perform A result, A plus B bar. Since we give as external carry 1, so in this case we give as 0, so it will be 0. But in this case we give as 1, right? This is equivalent to what? A is nothing but A minus B, right? So this A minus B operation is done with m equal to 1. If m equal to 0, addition operation is performed in this hardware. Also, we have one more bit called AVF. So this AVF is used to indicate the overflow. Okay, this AVF bit is used to indicate the overflow. Okay, now this is the hardware which is required for implementing this implementing this addition and subtraction. Let us deep dive into the algorithm. See, I told that the algorithm is represented with the help of a flowchart. Okay, now let us try to visualize the flowchart and let us try to understand this flowchart. Okay, see here, first of all, let us see this. So we need to perform add operation, okay, and we need to perform subtract operation. Okay, now this according to the terminology, the number a plus b, if you want to perform a plus b, the a is called augend and b is called addend. Okay, so augend is taken in the a register whose sign is stored in the as and magnitude is stored in the a. Similarly, b is taken in the bs is taken, sign is taken in the bs and b is taken the magnitude. Now I need to perform addition. This is the objective. Similarly, in case of subtraction, we call a as a minand and b is the subtrahend, right? Now similarly a is taken in the a register, as is taken as a sign, b is taken in the b register and bs is taken in the sign. Now what is the first operation, Andy? What is the first operation we perform? The first operation we need to perform is whether we need to perform the addition or subtraction. So in case of addition, add operation, what is the meaning? In case of add operation, if the signs are equal, we need to perform the addition. If the signs are different, we need to perform the subtraction. So how to compare the signs, and ikkada? So we need to compare the signs. We need to compare here the signs based on the as and bs. Now if we perform XOR operation between the as and bs, you know that. So as and bs, if we perform the XOR operation, what we get? So if we perform the XOR operation between as and bs, what we get? 0 0 0 1 1 0 1 1. So if the signs are equal, we get this 0, right? If the signs are different, we get this 1. Now if the signs are equal, if this XOR operation is 1, meaning that signs are not equal, right? If the XOR operation is 0, meaning signs are equal. Like this, based on the XOR operation, what I can do, I can compare the signs of these two numbers and tell that whether the signs are equal and whether the signs are not equal. So in case of addition operation, if the signs are equal, we need to perform addition. Similarly, in case of subtraction, if the signs are different, in case of addition, if the signs are equal, in case of subtraction, if the signs are different, we need to perform the addition, right? So how to represent addition, Andy? Just represent a plus b with this micro operation and the result is stored in a and the external carry is stored in the e, right? Now while performing the addition, we need to take care about the overflow. So what is the overflow, Andy? Overflow in this case, this is unsigned numbers, right? So in case of remember here, so these are the sign magnitude numbers. So in this case, if we are performing addition, there is a chance of having an overflow, right? So overflow here is indicated by the fact that e equal to 1, right? So if e equal to 1, there is an overflow, right? So overflow here is that we have only, for example, if the a is a 10-bit register, right? If we get an extra 11-bit, so that extra 11-bit we cannot hold in the a. So that 11th, so we tell that we got an overflow, right? So whenever this overflow is there, we need to indicate the user that we have got an overflow, right? So that indication is done by moving the e to the AVF flag, so that if AVF will be set indicating that we got an overflow, so that the programmer who is using this hardware can appropriately, he can take that action, right? He realize that there is an overflow, so he need to interpret that result in a appropriately, right? That is a meaning. So what we do, whenever we get this E flag, right, E flag we keep to the, we carry to the overflow, so that whenever the E equal to 0, so AVF will be 0, so that no overflow, right. Similarly, if E equal to 1, AVF equal to 1, indicating that there is an overflow, right. So this we need to take it. This is what the addition, Andy. This is what addition flow, right. Now let us see the subtraction. So when to do subtraction, sir? So we need to do the subtraction when in the while performing the addition if the signs are different. Similarly, while performing the subtraction if the signs are equal, right. While performing the addition if the signs are different, while performing the subtraction if the signs are equal. In both the cases, what we need to do, we need to perform the subtraction. Listen here. So here what we do is, first we perform A minus B, right. So what we do, actually we need to perform, remember here, how what are the three cases I need to deal with subtraction. So I need to, if A is greater than B, I need to perform A minus B. This is the first thing. If A is less than B, I need to perform B minus A, right. If A equal to B, I can do A minus B, right. So these three things I need to take care here while performing the subtraction, right. Now what I do here, instead of comparing before, right. So this decision of performing A minus B, B minus A minus B, when I know, once I compare and know that whether A is greater than B, I need to do this, or A is less than B, I need to do this, or A equal to B, I need to do this. So first I compare, then I can do this. But here I am doing in a different approach. What I do is, instead of doing this directly, I perform A minus B. Let us perform A minus B, right. How I perform A minus B? A plus B bar plus 1, right. You know, just now I explained how can we do this in the hardware, how can we implement this micro operation in the hardware, right. So you know that while performing the subtraction there is no chance of overflow, right. This I discussed while discussing the overflow. There is no chance of getting an overflow when we perform the subtraction. Only during the addition we get an overflow, right. So since we don't get an overflow, we make this overflow flag as 0, right. So this we perform. But now what I do is, once I perform this, I know that if I, based on this end carry, what I can interpret, if this end carry is 0, right, just now I explained in the beginning of this lecture, if the end carry is 0, the meaning is A is less than B. If the end carry is 1, A is greater than or equal to B. So let me first perform A minus B, then I interpret that whether A is less than B or A is greater than or equal to B. So once I do that, what I can do, if A is greater than or equal to B, very, very good, right. If I get an end carry, very good. Whatever I want to perform A minus B, I already performed here, right. I already performed here, right. If A equal to B, if A is greater than or equal to B, I did that. But here again two cases, whether A is greater than B or A is equal to B, right. So if A is equal to B, what I told, I I need to take care, I get a pass to 0. For that what I do, I just put AS as 0 to ensure that I get a pass to 0, right. Okay, this is okay, very good. Now if I don't get an end carry, what is the meaning? A is less than B. So in this case what I need to do, I need to do B minus A. But what I did A minus B. So what I need to do, how to get B minus A from A minus B, just take 2's complement of this value, right. So if I want to get B minus A from A minus B, just take 2's complement. How to take 2's complement? Already this B minus A result is A minus B result is available where? A minus B result is available in the A, right. A minus B result is available in the A. Just take 2's complement of A. How to take 2's complement of A? Take 1's complement and perform add 1. So this ability is integrated to the register A, right. So just take the 1's complement of the A and add 1, increment that, so that you get the 2's complement of A. So that's what is represented here, right. So let me once again let me repeat this. So what here I am trying to do, first in the first stage I am taking decision that in case of addition operation, whether I need to perform addition or subtraction. If the signs are equal, I am performing the addition. If the signs are different, I am performing the subtraction. Similarly, in case of subtraction, if the signs are different, I am performing the addition. If the signs are same, I am performing the subtraction. So how to perform addition? Just add two values and the result will be saved in the A and the carry will be saved in the E. If the transfer this E flag to the AVF so that to indicate the programmer about the overflow condition, right? Similarly, you perform subtraction. How to perform subtraction? If the signs are different in case of addition, if the signs are equal in case of subtraction, perform the subtraction. How to perform the subtraction? So we are performing A minus B here. How we are performing A minus B? A minus B we are performing using the 2's complement method, right? Once we perform A minus B, then based on the end carry, I interpret that whether A is greater than B or A is less than B. If A is greater than or equal to B, very good. I need to perform A minus B. I perform A minus B. The result is available in the A. So but again I need to check whether that result is 0 or not. If that result is 0, ensure that it is a positive 0 to avoid the negative 0. Okay. But if the carry is 0 indicating that A is less than B, I need to actually perform B minus A, but I perform A minus B. So the result is there in the A. So what I do to get A B minus A from A minus B, what I do, I take the 2's complement of the result. For that, just perform 1's complement and add 1, right? Also the sign must be reversed. So this is understood, right? The sign of the result, the sign of the must be so right, you did A minus B, just we have seen, right? Why sign inverse? So we need to take the complement of sign of A. That's what I told in the algorithm, right? If the A is less than B, what is the result? What is the sign? Just perform B minus A, right? And take the complement of sign of A, right? That's why I take the A complement. Okay. So this is what the algorithm for okay, addition and subtraction when the numbers are represented in the sign magnitude form, right? Now let us proceed with this. Suppose if the numbers are represented in the 2's complement form, right? So if the numbers are represented in the 2's complement form, so here the that if the numbers are represented in the 2's complement form, let me explain this with a simple example, then we proceed, right? So for example, let me explain the process of addition and subtraction in the 2's complement method. So let me take the 4-bit numbers for ease in understanding. So for example, in 4-bit number, that, okay, so we are representing the sign numbers. So in 4-bit numbers, that you represent with -8 to +7, right? In the 2's complement form, right? Like if we take 2's complement form, this is the range I get, right? Now how to perform addition? For example, I want to perform, okay, -4, okay, -4 minus okay, -4 -2, okay, what I want to get, -6, right? So how to do this? Represent this negative number, right? I want to do, okay, addition, right? So -4 plus -2 is -6, right? So how to do this? So first you represent +4, right? So what is +4? 0 1 0 0. What is -2? 0 0 1 0, right? Now since it's a negative number, take the 2's complement of it, right? What is 2's complement of it? 0 0 1 1, right? 0 1 1 1, right? So this is a -4 representation. This is the -2 representation. Once I take this, what you do? You perform the addition, right? 0 1 0 1 1 1. What you take the end carry? Just ignore the end carry. So this is the result, right? So how to interpret this result? So since this is a negative, this is a sign is negative, so you need to take the 2's complement to interpret the magnitude. You need to take the 2's complement of 1 0 1 0, right? So what is the 2's complement of 1 0 1 0? Take 0 1 1 0, right? So what is this? This is nothing but -6 in decimal, right? This is a binary, this is in decimal. So this is how you need to perform the 2's complement thing. Here this is the thing. So what we are doing here, so whatever the negative number we are having, so that negative number represent in the 2's complement form, just perform the addition, that's it. Even in the subtraction, whatever the negative number you have, you convert into 2's complement, then perform addition. right? Now in this process, suppose you need to understand what is an overflow. Okay, so let us see here. So for example, see here in this case what we got, in this case there is no overflow. Why no overflow? See here. So what we need to do is we need to see this carry into this and carry out of this. So these two carries are equal here, right? So that is the reason why we did not get an overflow. Okay, so suppose we get we'll see one overflow condition. For example, let us take this example. I want to describe the example where we get an overflow, right? So okay, let me take this +6 and +7. Okay, so I get a here I get a +13, right? So +13 cannot be represented, right? So let us take this +6, okay, representation. So 0 1 1 0. So +7 is nothing but 0 1 1 1. So 1 1 0 1, right? 1 1 1 0. So here you can observe here that the carry out and this carry, this both are not equal, right? So this both carries, the carry into this and carry out of this, these both are not equal. So this indicates a overflow condition. Okay, so in the previous example, as we see that so what is actually the overflow here is, so actually using this 4-bit numbers, we can only able to represent this, the range is -8 to +7, right? So but actually we are getting the result as +13, which cannot be represented. So that is the overflow here, right? So but in the previous case we get the -6, which can be represented in this range. So that's why this is not an overflow. But how to identify that? So how to identify that is, we need to look into this both carries, carry into this MSB bit and carry out of this MSB bit, right? So if this both carries are equal, this indicates that there is an overflow, there is no overflow, right? If the both carries are different, that indicates there is an overflow. So how to identify this? So let me give this 2 bits to an XOR gate, right? If these 2 bits, if I give to the XOR gate and inspect that, if the XOR gate output is 0, means what? When we get XOR gate output 0, if these both are either 0 or either 1. So if these both are equal, we get 0, means no overflow. Okay, but if this XOR gate output is 1, indicating that this carry and this carry both are unequal, indicating that there is an overflow. Overflow means the condition where we have only 4 bits, we got a more result more than 4 bits, so that we cannot store that result in the 4 bits. So how to avoid overflow? The only way to avoid overflow is that we increase the size of this register. Instead of storing the 4 bit, if we can able to store 5 bits, there is a no overflow. But that is not the case, right? Since in the computer the hardware is fixed, right? Since the hardware is fixed, so we need to take care of this overflow, right? So generally this overflow, we have this overflow flag to indicate there is an overflow, right? Now for this 2's complement representation, if we want to implement in the hardware, right? Let us see the hardware for this. So this is just a simple hardware. Take one number. So here you know that, right? So we no need to represent the sign in a separate. This is the 2's complement representation. The sign is integrated with this. So the entire number is stored in the AC register, one number. The another number is stored in the BR register, right? So this complementer and parallel, you know why complementer? For performing the subtraction. Before performing, I need to take the complement. For that we have a complementer. So here I no need to consider the carry. We ignore the carry, so we don't have any E bit here. So since I told that we need to take over the overflow, we have this overflow to indicate the overflow. So generally this overflow is implemented with XOR gate. So the XOR gate output is connected to this overflow flag, where, right? So this is what I told. So let us see the algorithm for this. In case of addition, what we do? Just we take one number in the AC, another number in the BR. Generally this terminology is occend and addend, right? So just we perform addition, right? So AC plus BR, and the result is stored in the AC. No need to consider the carry, right? Even if we get a carry, just we ignore it, right? And if we get a overflow, we indicate that with the overflow. Just now I told how to perform the overflow, right? Just we take these 2 carries and connect to the XOR gate. If the XOR gate bit is 1, that is a overflow. If the XOR gate bit is 0, no overflow, right? Similarly, subtraction, how we perform? Take one number in the AC, another number in the BR. So whatever the number in the BR, take the 2's complement of that number, right? So if I want to perform AC minus BR, right? So AC plus BR bar plus 1. So also assume that this number already, if it is a negative number, I'm assuming if AC also a negative number, I'm assuming that it's already there in the 2's complement form, right? I'm also for BR, if it is a negative number, it's already there in the 2's complement. So what do you mean by that? For example, if I am performing this subtraction, minus 5 minus 6, I am assuming that the 2's complement of minus 5 is already available in the AC, the 2's complement of minus 6 is already available in the BR. This is what the assumption is, right? Similarly, if I want to perform minus 5 plus minus 6, what is the meaning? So this 2's complement of minus 5 is already available in the AC, the 2's complement of minus 6 is already available in the BR, right? Now once I perform this addition, right, subtraction using this 2's complement, I ignore the carry, right? Again I indicate the overflow. So this is the simple algorithm for the 2's complement method, right? So this is the conclusion. In this lecture, we have seen that if the numbers are represented in the sign magnitude form, how to perform addition and subtraction. We have defined an algorithm for that, and we have seen the hardware and algorithm for that. Similarly, if the numbers are represented in the 2's complement form, how to perform addition and subtraction. So thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.